Yeah, so, thanks. So, before starting, I have a general disclaimer that I'm not an expert on this topic, and I'm actually learning while telling you about it. So, I study and then what is there this week, especially this lecture. Next, Florent will start. Florent is a better expert than me. But are you an expert or medium level expert? So, because it's an important topic, it's a relatively new topic than classical graph theory, and we want to learn it also, so that we can do research. We can use it in our research, or we can do. So, it also gives me, so it helps me when I study and also tell you about it, because I can ask myself some questions which I wouldn't have normally asked while preparing. So, in fact, some of you may be more expert than me. Please correct me if I am wrong and ask questions. Okay? Okay, let's start. There will be a little bit of repetition than to what happened last week, just to maintain the continuity and also consider context. So let's start with something called. Let's start with the definition of average degree. So what is average degree of a graph? AB of G. So it's exactly how its name is suggested. It is B in G. So you sum all the degrees and take average. There are V vertices, V of G vertices, that's all. But because of the handshaking lemma, this has a nice form, and I can express it without even mentioning degree. Okay? So this thing is twice of E, right? Summation degree because of the handshake. So I can say something like this. Okay? So this is average degree. When you speak about sparsity, like how a graph can be sparse, so it makes sense to speak about average degree. But in the very first lecture, Florent also mentioned it, and then told you that this is not a very good measure of sparse. Sparse means you have less number of edges. Dense means you have a lot of edges in your graph. Yeah, speaking about simple graphs. So in average degree, what may happen? It may be a bit fake measure, because you may have a big click here. So there may be a Kn sitting here, and then you may have, I'm keeping the graphs connected, very, very long paths, and many of them. So, yeah, so cricket analogy, it's like Karun Nair, who had a triple century and many very less scores, and the average is less than 30. So this can have something like that. But it will hide this very dense chunk inside it, and this average degree will still be low, right? So we don't want this kind of things. We want something better. Okay? So one of the better measures that we have seen is degeneracy, because every subgraph has something small, right? And that's the next definition that I would like to give. But maybe there. Actually, you know the definition of degeneracy, so I will give you a proposition following equivalent. So that means the following are equivalent. I'm going to make a few statements and all of them are equivalent. Okay. So number one is for all H subgraph of G, minimum degree of H is less than 1. The second one is there exists vertex ordering V1, V2, Vn of G such that neighborhood of Vi intersection V1, V2, Vi minus 1. This is bounded and this is bounded. Okay. For all I. Yes. For all. Okay. So for all I from 1 to 12. Okay. The third one is if you keep deleting degree less than equal to k vertices from G, you get empty graph. So like empty graph and no vertices. Okay, so it's not very mathematically precise, but what I mean is you take your graph, look at any vertex which has degree less than equal to k, you delete it, and then your graph is modified, right? In this new graph, if you find a degree less than equal to k vertex, you delete that, and you keep doing that. But you are not looking at degree less than equal to k vertex in the original graph. So every time you delete, your graph gets modified and you keep deleting it. And finally you would have deleted all the vertices. Okay? This is the third one. The fourth one So what am I saying? You orient the edges. So that is, instead of edges, you put some arcs. You put a direction on the edges. That is the orientation of G. There can be many orientations of G, but you can find one orientation such that all the outgoing arcs. So there is something incoming and there is something outgoing. All the outgoing for each vertex, maximum is k, not more than k. Okay? So the definition is G which satisfies one of these properties, and due to the proposition, it is all of these properties. If it satisfies one, it satisfies all. This G is K degenerate. So usually K degenerate graphs are defined using either the first one or the second one. But it's good to know that it has some equivalent formulations and they become important somewhere. Okay.
One question is,
Yes.
is there any upper bound of K when we are talking about K degenerate, so that we can say the graph is sparse in terms of number of masses n?
No, I mean natural upper bound is delta.
Small delta.
Capital delta. So maximum degree is always a upper bound. Because
when we can say this is sparse?
no, that is a bit no. You have to wait for that. Okay. So there are different ways people have defined sparse. So we are concentrating on one particular way, which is boundary expansion, and that definition I think doesn't come directly from degeneracy. So there is more details. There are some more details. There is relation. Okay, and then I have a proposition which says. So by the way, we will not use average degree almost at all. Maybe for some calculations, that's all. So, proposition. And the proof of this proposition will be exercise. It will be one of the tutorial questions. Yeah. So G has degeneracy K implies chi of G is less than equal to K plus 1. So how do we do that? So which one do you want to use? Which of the properties? Second one, yeah. So these are your vertices, okay? You have taken the second definition and you have ordered them. Now, look at V1. V1 doesn't have any neighbor. It's a special one. So you put color 1. Now, and you keep putting some colors. Maybe these are adjacent. If they're adjacent, you put color 2, or you put color 1 if they're not adjacent, right? So we will use a greedy algorithm, very basic greedy algorithm. So we will look at Vi. Everything before it is color. So V1 to Vi minus 1 is already color. Now I will look at Vi. I will see what are its neighbors and what colors they have got. The minimum color it did not get, I will put that color. Okay? But Vi, how many neighbors can it have here? So maximum K. So no matter how many neighbors it has, less than equal to K colors are used. But I know I can use K plus 1 colors, so I will have at least one color left with me. And whatever that color is, I will put it. and continue coloring the graph this way until Vn. So I will have a k plus 1. It's quite simple. Okay. So from here we can also say that the trivial part of Brooks' theorem is true, that every graph is d plus 1 colored. And in Brooks' theorem, then you say, actually characterize which exactly are the graphs which needs delta plus 1 colors, and those are complete graphs and odd cycles. Exclude them, then every graph is delta colored, connected graphs. Okay. But now, how low can be, so of course you know, I mean this is not tight, but how low can it be? Let's say for planar graphs, so planar graphs has degeneracy what? This we have proved. Fine. So immediately from here I have a 6 color theorem. Definitely I know it's 6. But we have already proved the 5 color theorem in class. So we know it is 5. And in fact, because of the 4 CT, I know that it is 4. So it's strictly less than the degeneracy, right? Degeneracy plus 1. So this is sometimes also called the coloring number because of the property. But we will mostly not use that term. But you can see, encounter that term while reading papers. Okay. How small it can be? Can the gap be arbitrarily large? Some graph where this degeneracy is very small, but the chromatic number is.
Yes, we saw that example. From 5 cycles, we got another cycle. Like you take that graph and then we can keep on increasing like that.
Yes, that is standard. Okay. So, yeah, those kind of things. No, but there the degree number was, yeah, peak number was super. But anyway, the other thing is that planar graphs are very special. I can find degeneracy 5 graphs which are 6 colored. So what is it? Tell me one degeneracy 5 graph which is 6 colored. Like chromatic number is 6. K6, exactly. So K6 is a graph which has degeneracy 5, obviously, and it has chromatic number 6. So Kn is always a graph which attains this equality. So it cannot be improved in general. Okay. We don't define degeneracy usually as optimal thing. So for any k it is degenerated. So but the minimum is called the coloring number. So how about K33? What is the degeneracy? And chromatic number Kn, degeneracy is n, chromatic number is 2. So I can have graphs with arbitrarily high degeneracy but low chromatic number. Okay? Kn is next. We'll come back to this, come back to degeneracy, but right now I want to define something called maximum average degree. Abbreviation is MAT. Okay. So here what we are trying to do, we are trying to counter the problem that there can be a big chunk of dense graph hidden inside your big graph, right? But how do we do that? MAG is actually maximum. So this is 2E by Vg, that is the average degree. So it is 2 H instead divided by Vg, sorry, Vh, where H varies over all graphs. You can also define it like induced subgraph, because induced subgraphs will have the maximum degrees, the maximum average degrees always, most number of degrees, but both are. Okay, so this is the maximum average degree. So this looks like a better, a measure for sparseness. If you have no maximum average degree, that means nothing very big is hiding inside your graph. But this is also not very good, because remember what we are doing, we are also thinking about minors. Right? We want my graph not to have dense minors. Okay? So for example, now let's see.
So there's a question from the last part. You had a minor model.
Yes.
So how are the related M1 into M3 M in the minor model? What was that?
I will actually redefine it, so I'll come back.
Relation between maximum average degree of a graph and its k.
Yes, there is. In front of me. So maybe you can also say I think I should say that. So this is color number of G. This is a CL. Color number of G. So if you optimize the degeneracy for minimum K, so the minimum K for which G is K degenerate is the color number of G. It is different from chromatic. It's just called color number. So it's CL, not chi.
I think it's also called degeneracy. It's also called a degeneracy.
Degeneracy can be K, so a graph can be K degenerate
Yes,
and
the degeneracy
K plus
is
1
minimum
degenerate.
K such that.
So not always they optimize. In that note that you sent me, they optimize and call it DEG.
Yeah, I've usually seen that, but
Okay.
it doesn't matter.
They have this separate name because of the convention that you want to say that your graph is K degenerate, but you don't know if the K is minimum or not.
Your K degeneracy means at most K.
Okay.
Degeneracy K
So-
is exactly.
So this is also degeneracy the way you were suggesting. So I think there are two versions. The same thing I'm calling color number. Now, before answering Supraja's question, let's answer her question. So, this is what exactly we were asking. So, color number or degeneracy is a lower bound for maximum average degree, and twice of that is an upper bound. So, it's sandwiched between color number and twice color number, maximum average. Okay. So, that makes it more important, because you know, if you know degeneracy, you have a good estimate of man also. CL, that is CL. Yeah. I have to be consistent with that. Okay, so how do you prove it? How do you prove the first inequality, let's say? Yes? So, you see,
So minimum is less than average.
man is definitely, this is trivial, right? Okay? But then, your average of something is bounded by t, so the minimum number will be less than it, right? So, definitely, you take any subgraph of G, you go to maximum average degree, that subgraph is A.
Man is greater than equal to
Which one?
Man is greater than equal to at ADG. We will give the max of positions.
So, let's say, man of G equals to T, and T may not be an integer, it can be anything, it's average. So that means, this implies there exist, okay, now, take any subgraph h of G. We know EH by VH is less than equal to T. So that also means that 1 by VH summation degree V inside H for all VH is less than equal to T. If the average is less than equal to T, there exists at least one vertex. So there exists V in VH such that degree of V is less than equal to T, which again implies small delta of H is less than equal to K. And that exactly is my first definition of degeneracy. Okay? So this inequality is true. Okay? But the more involved one is probably the second one, not too much, but can you tell me how it is done? Which definition you want to use first of all? So I want to say degeneracy is K. So let's say that. Let
Degeneracy is less than equal to delta capital density.
that is true, but that doesn't help, right? It will be very less also. Let's say, or equal to K. K is an integer. Now you have to say that man is less than equal to 2K. Right? So in other words, you have to show for any H in G to H by G is less than equal to K, right? Sorry, 2K.
And VH.
Thanks. Yes. So we have to show this, right? So now one definition of maybe that's okay. It's possible. I think you can use any, but I want to use the third one. Okay. So third one is what? We have this something, we peel off, then you have something else, you again peel off, you have something else, you peel off, okay. You eliminate one vertex at a time. But when you eliminate one vertex, how many edges are you sacrificing? Or how many edges are you deleting?
K.
Maximum K. Okay. So, it's okay in the third definition. So, total how many edges are you deleting? How many edges are you deleting? So, it is K in less than or equal to K in each step, and so it will be N,
Minus 1.
N K is okay. Also, edges in total. Okay. So that is the number of edges that this is the now you don't have any edge, any vertex in your graph. So this is nk is a upper bound of your number of edges. So what n is the number of vertices. So what I can say from here is number of edges in G, or in fact in H, is less than equal to number of vertices in H times K. Right? Because even if you don't take G, even if you take H, you should still be able to do that. Okay. Now, from here you have EH divided by VH less than equal to K, but you want twice of this, right? So in both sides you multiply 2 and you get this. That's what you wanted to prove, and that's what proves this inequality. Right? So by what Showman told, maybe you can do a slightly better one. Okay? Even if it is n minus 1, right? I don't know, I mean it's slightly better, but I think it won't matter. Asymptotically. So it's okay, this proof? Yes? This one? Okay. So this one is you fix the map, okay, and then you say that you take any subgraph of G that has that has this quantity is bounded by G, okay, but this quantity is the same as this kind of a thing, average of the degrees. But now you have n vertices, and the degree sum by n is less than t, less than equal to t. So is it possible that all the degrees are more than t? It's not. So at least one degree will be less than t. Now you have set out with a subgraph of G, and it can be any subgraph. So any subgraph of G has at least one vertex which has degree k or less. That means minimum degree of H is less than equal to k. That's the first definition of degeneracy. So you have degeneracy less than equal to k. So it's okay for everyone. Please interrupt me and ask, because I'm going slow, and I think Flohon will use a lot of these things.
Can you repeat this one?
The second one.
Yeah.
Okay. So you think about this. You have your graph. Now you are deleting one edge, one vertex, And according to this, that vertex has degree less than equal to k. So you are also deleting k edges. Then you have a modified graph. There also you can find a vertex which has degree less than equal to k, and you are deleting it. So in the next turn also you are deleting at most k edges. So you are keeping on doing this until the last vertex. Okay. So you have deleted n vertices, and each time you have deleted k edges. So nk is the upper bound for number of edges. That's what is written
Number
here.
of edges you deleted.
Yes, but now there are no edges left. So that is you have deleted all edges. Basically. So EH will be less than equal to VH. This is n and k times k. But now you do simple algebra. EH divided by VH times 2. So times 2 happens there also. And this is the quantity you wanted to know. This is for any subproblem. Sorry?
So the calculation will, this process will be in the G, right?
In H also we can do, because if G is degenerate, then H is also degenerate, right? K degenerate. Right? Any subgraph is also K degenerate. You take any subgraph of H, that is a subgraph of G as well. So with the first one, any subgraph of K degenerate graph is also K degenerate.
So we are taking the verses for K at most K.
At most K. In H now.
So in particular, for a particular subgraph H, might not be always a vertex degree at most.
It will be, because use the first definition then. So G is K degenerate. Its subgraph H is K degenerate, is what I'm going to prove. So G is your graph, K degenerate. H is a subgraph. So what does it mean by H is K degenerate? Any subgraph of H, which is J, should have minimum degree at most K. But any subgraph of H is also a subgraph of G. So by this, it also has minimum degree less than 2. Right? Okay. Now, so MAD and degeneracy kind of, you can say that if MAD is a good measure of sparsity, then degeneracy is also a good measure of sparsity and vice versa. So, now let's see. Well, I have taken K4, I could have taken any complete graph, but let's do it with K4 first. Tell me what is the degeneracy of K4? 3. Let's reduce it a little. Let me subdivide each edge once. Now what is the degeneracy? 2. If I take a Kn and do the exact same process, like each edge, what is the degeneracy of Kn? N minus 1. So K100 is 99. But I subdivide every edge exactly once. What becomes the degeneracy? 2. So a MAD 4 graph, MAD less than equal to 4 graph, can hide as big Kn minor as possible. And Kns are quite dense. So it can have a very huge dense minor. Right? You don't want that, because you saw already that the minors are very nice things, and you can you want to characterize many things in your graph using minors. So if minors are dense, then you are not studying sparse graph. So you want to exclude these kind of things also. Okay. I think now that gives you something called shallow minor, that motivates the definition of shallow minor, which is the new thing that we will start today. And Flohom will extend it later on. Or similar things. Okay. I will define minor model with formally. And probably then change this to a shallow minor. Minor model phi. So phi is some function. I'll tell the domain and codomain all these details later. So phi of h in G. So h and G are graphs. Is a function such that so the domain is vertex of each. Yes. The codomain is connected subgraphs. So this phi, which is called the minor model of H in G, is mapping each vertex of H to a connected subgraph of G. Okay? And that mapping satisfies some condition, of course. Satisfying number one. Find your U intersection, or to be very precise, I think I should be precise on this, it's important. So, these two conditions. So I will translate these conditions into English. Okay. So a lot of symbols right now. They are not bad symbols. So what I'm saying is, phi is taking your vertices of H to some subgraphs of G, but those subgraphs are distinct. That's the first condition. So what does it say? So phi of U is a graph, subgraph of G. Look at the vertex here. And another distinct vertex V. For that, phi of V is another subgraph of G, right? But these two subgraphs are disjoint. That's the first condition.
Okay. V at the representatives of that graph. U and V.
No, U and V are in VH. So you have two graphs. H is a minor of G. So from H you have a mapping to the connected subgraphs of G. Okay, we'll see examples also. And then what we are saying is, if U and V are adjacent in H, then there exist U prime and V prime which are adjacent in G, but U prime belongs to the subgraph of U, like phi U, and V prime belongs to the subgraph which is corresponding to the vertex V. Okay. So let's look at some examples. Actually, let's look at the example we have already. So we subdivide our K4 and we have said that this has a K4 minor, right? So this is my G, and I will draw one H also. H is, this is G, H is K4. Let's say A, B, C, D. Now I want to find the mapping. This is a connected subgraph, right? Should I use a different color? Or? So this one is phi of A. Okay. Next I can say this guy is phi of B. Then I can take this as phi of C. And this one as phi of B. Just to say that this binary is nothing special. So this is how you can visualize the mapping. Now check the properties. The first property, of course, these four things do not have any common vertex. So first property is immediately satisfied. And then the second one, so they should all have edge with each other. So A and B are adjacent there. So this yellow vertex and this white vertex, they are adjacent. And A and D, this yellow vertex and this white vertex are adjacent, and so on. Okay? So you can see all the adjacencies.
So here that U dash and U dash, so there should exist one U dash and
Yes, in G. So basically what I am saying is, if you take the connected subgraph of U and connected subgraph of V, they must have an edge inside G. Right. So things are okay? Yeah?
So this is basically a Bramble, right?
This is?
Basically a Bramble, right?
So, parallel
No, they are touching, right? I mean, that the second definition of touching, like they have an edge.
brambles can overlap.
Yeah, they can overlap, but this is also.
This one is a brand.
This one is a
particular example. But not, yes.
This is just the same definition in your there exists vertex partition at each of them.
Yes, exactly same. Because I called it, one is he also asked. And then add one more line to the D shadow. Okay. So I can erase this. Yeah, this is the exact same definition as minor I gave before. I gave two definitions, this is the second one. But it's a bit more formal. I did not give it this formal. That's it. Now,
So the minor one you need a sequence of subgraphs. Each one is to each end.
so this is a minor. Now you can use this definition. So basically the sequence is like, if you index the vertices V1, V2, Vn, then phi of Vi is your capital Hi. That's all. It's the same definition but in a different language, in the language of functions. This is more formal. D shallow minor this phi v are called branches. Of G, if there exists minor model phi of H in G such that the branches, that is phi v, have radius so now I'm looking at a minor model where you have all these components, but these components are not very wide spread, in the sense they have a bounded radius. Okay? They are somehow kind of close to each other. So, examples again. Yes.
What do you mean by radius? Is it like triangle?
Yeah, I'll come to that. So yeah, let's define those things also. And then I can erase something there, something here, and here. So let's see. Distance v equals to length, which is number of edges. So, distance between u and v inside a graph is the number of edges on a path which is connecting this, and you minimize that. Then radius g, this will be finite only for connected graphs. This is again minimum.
Max mean.
Max mean.
Max of all distances.
The min max.
Max mean. Distance already minimum.
Distance is the right.
Max.
So minimizing distance v.
No, you just write distance UV. It is
Say again?
max of all distances.
Distance is already determined.
No, that is dimension.
Huh?
That is dimension.
This 5
So it's mean max mean.
Yes,
This
Mean
right.
max of distance.
but I am doing radius.
By
So it's not always by 2.
2 flow.
No, it's not always. It's not always.
It can be equal
So
equal to dimension.
yes. So like for Kane, diameter and this is the same radius.
That is
One.
ceiling.
No, it doesn't have that.
The radius is the minimum.
So
eccentricity.
there is one, you have to vary the vertices
Yeah, you take
and
this
you have to
one,
cover everything. So
minimum.
minimum, first it will be minimum over all u, all v in So basically, you will stand on one vertex and then see how far things are. You take the farthest thing from you, that is your distance from this vertex. Now you will vary your vertex and try to minimize that. So that vertex will become a center. For an example, you can see a few examples. So tell me which one is your good vertex. So if you stand on this vertex, then what is the farthest distance? 1, 2, 3, 4, 5. Doesn't work. If you stand here, then this side is 1, but that side is 1, 2, 3, 4. Doesn't work. Maybe, I mean, till now it's 4. 2, 1, 2, 3. Here also it will be 2 and 1, 2, 3. So the radius is 3, and both are centers. Okay? If you increase 1, then this will give you 3, and only that will give you 3. Others will give you more than. So this one, for example, 2 in this side, but 4 in that side. Okay? So you are basically varying the vertices, and now you are varying the other vertices and looking at the distance. So distance with itself is 0. So this is the radius will be 3 in this case. If you have a 5-cycle, for example.
Everyone is in a session.
Yes, but what is the maximum distance you have to travel from here? 1, 2, 1, 2. You are able to cover, if you go, so basically you can think like this. You have a network, you are standing on a node, and you are asking this question, how much do you have to travel to reach everything? Okay? And then you minimize that over all the words, you vary it over all the words. This is the definition of radius clear because it's very important. It's very integral for us. Okay? The definition is written correctly. So if it is not clear, please tell me, we can do some more examples. Do you know what is a metric? So metric is kind of a measure of distance, but it has a mathematical definition. So you have a space and you have elements, and it will be something like d of, I will say, xy. Okay. It's a function from space, cross space to positive real numbers, usually, not integers, but real numbers. And then it has some 3 properties. One is that it should be symmetric, and then the second should be, like, it should be always positive, and equality holds if and only x equals to y, and then you have triangle equality. Less than equal to dxz plus dzy, right? So the distance, graph distance on connected or any graph, it gives you a metric. One exercise you can do at some point of time, maybe we will put it. That on directed graphs, it doesn't give you metrics. If you look at the distance as you are following the arrow and where can you reach, it's not symmetrical. It will become something called a quasi-metric. Okay, so there's this part also. And this one. this is your graph. Now find K4 minor and try to make it shallow as possible. So shallow, the English meaning is that there is water but not very deep. It's the opposite of deep. So if you want to find a shallow minor, so you should try to minimize this d. Because the theories are dependent on this d, and if you have small d, the algorithm runtime will be small. So first of all, you see a K4 minor. Yes. Tell me again.
There are two I can see.
A, G, F, E. This one. And I. No, I mean I include this. I here.
I and H also. Below.
So you want me to
H also.
H also. Okay. Okay. Fine. This is your one. No, but I want a minor model. Sorry, not just a minor. The minor model. Okay. So I want 4 connected subgraphs, which will give you the minor model, and then you can speak about the depth, because we will look at each one's radius. So this gives you a K4 minor because you will contract. That is okay, but I want a minor model. So can you please tell me the minor model? Any minor model.
AB.
AB. You want AB to be more subgraph? Hmm? Yeah, tell me.
It can be AB, ABE, ABE.
Yes. ABE or AB?
is
AB. AB is 1. Then
another is C. I.
C,
BDI.
CDI,
CBD.
CDEI. Okay.
And the rest. G.
No, but you have to tell me 2 more.
Yes, F is yellow.
F is alone. Okay. F is
Yellow. And rest. G.
all of them? You want to take all of them?
Yes.
Fine. So do we have a minor? F has edge with all 3. This has edge with those 2. And these 2 have edge between them. It's true, it's a minor model. But how shallow is it? So this has radius 0, right? This has radius 1. What is the radius of this?
1.
No, it's 2. This has radius 2.
This is 1.
This is 1, because D. Okay. So 1, radius 1.
The other one is 2.
This is also radius.
How about this one?
2.
This has
One,
radius
one.
2, I think. Why? How?
From J. Yeah. This is
Either J or S.
from J.
No, this is 2. Right? Yeah. So, yeah, from G, of course, many things are far. From H, K is far. From J, L is far.
From G to K, distance is 3. Maximum distance is 3.
Yeah, so G is not the center.
G is not the center. Center is J or H, and it is 2. It is not 1. It's not a complete graph, so it cannot be 1.
I forgot the definition. From J to maximum distance is radius. J is the center.
You find the center. Yeah. From everywhere you look at the maximum distance, but then you minimize, varying the vertices. So it's a too shallow minor, right? Too shallow. So K4
Sunday,
is yes.
you can take
Wait. Minor of wait.
you can take K in that set. K in that set, Arab set. K in this set.
Wait.
There is one,
So
one set.
my claim is that we have a 1 shallow minor.
Taking K in that Arab set.
E, I, H.
It's yes, it is also one shallow. Yes, correct. So this is a one shallow mass also. Right?
Definition that there exists a branch which has radius less than equals to d, or for every branch.
For every branch. Such that the branches,
Then
I will make it such that
Well, you can write all branches.
such that all branches for all, it's a bit extra. Excuse me.
union of 5 need not be VG.
No. It's never said that. Never says that. So, you see, if I want to take union, then the same problem is there because you have a big cane and then you want to extend a very long path. So the shallow minor has to take that path and the radius will become big. So you don't want that. You want to say that it has a small shallow, like really a shallow minor. From one shallow minor or something. But, so this is a K shallow minor, the yellow one. And in fact the red one is a one shallow minor.
That is, distribution is uniform. It is minimum.
So my solution was this. Okay. So my solution was this. It's also a one shadow. Path, two path, and like three vertex path, and edge.
But AD is not needed.
No,
Not needed.
no. That's what Euler's comment was.
Yes.
Now, can you find a zero shallow minor? What is a zero shallow minor?
Q is not a subgraph itself.
Exactly. So, what is a zero radius graph? Just a vertex. So, can you find four vertices here such that they have edge between themselves? So, zero shallow minors will exactly be the subgraphs. Okay? So, I can write here that observation zero shallow minor equals to subgraph. Okay? So you actually manage to capture the definition of subgraph also using this zero shallow or shallow minor. But you see, there is, let's do some more examples actually. Let's do some more examples. Find the diamond minor here. try to make it as shallow as possible. Now, I think I drew all the edges. So if you want to draw it, you can come here and draw also. So you clearly see a diamond shallow minor, right? Like diamond minor. It's a finite graph, so shallow doesn't really matter.
This is
Yes, the minor is clearly visible, but now try to select some subgraphs so that it becomes shallow. Too shallow? Can you give me too shallow? Okay, tell me. This? Okay, here.
Improve the coherence and make it better.
Okay, same thing.
Improve the edge, make it better.
There you have to do a bit more, I think. Yes. Right?
That's not a planarity.
Improve one more vertex.
Yes, this one is included.
Another negative.
Ah, yes, yes, yes. So it's not connected. Yes.
You need to write down one. You
Left
can
bottom.
make the write down one.
This one?
Left bottom.
Left bottom.
This one?
No, no, left bottom.
Left bottom branch.
So this is not connected with this one.
No, say it again.
Left bottom branch and right bottom branch.
This branch.
They are not connected.
right side, right side.
One side. I have to draw. Okay. So now what do we have? Too shallow. So this one I can take as a center. This is fun. And this one is just a path. So yeah, so too shallow. So I wanted to give an example which is too shallow, but not one shallow. I will hurry the way, but I think it is a correct example.
Oh, one thing, from that one and that one,
Yes.
connection is not there.
No, because I want a diamond number, not K.
They'll negate two and it's
Time more.
Yes. Yes. Not K. I also wanted to give an example which is not complete graph, which usually they say. So this is a too shallow minor, and I cannot probably, because I did not check it exhaustively, most likely there is no one shallow or zero. Zero shallow definitely is not there. So there is no one shallow minor. Okay. Maybe one more example, and then we. So I will subdivide 6 times. You will start thinking about it. Of course, there is a K4 number, it's clearly visible. But how shallow can we make it?
Three shallow only.
Okay, tell me your solution.
From each of them, take 3 neighbors, radius 3. From each of the vertices, radius 3. Radius 3.
think that's the best you can do, because you have to take, for example, this one in one of the, so you have to take the big degree vertices in 4 different subgraphs. That's obvious. And once you do that, once these two are in different subgraphs, you have to kind of separate these 2 parts of the connection. And the best you can do is 3, 3. Otherwise, one will become 4, another will become 2, but 4 is bad already. So this is 3 shallow. In general, if you take a complete graph and make it, like subdivide each of its edges by 2k many vertices, so 2k times. If you put 2k vertices, so it will be a k shallow, right? You can always do that. So that's a general example. I think it's kind of okay now. Yes, you understand what is shallow minor, but if I say that H is a shallow minor of G, if it is D shallow for some finite D, then it's nonsense, because you give me a graph, if it has a minor, then it is also a shallow minor. Doesn't mean anything, right? It doesn't make sense. But for it to make sense, we won't be defining it for a graph in particular. We will be defining it for a class of graphs. And then it will start making sense. And we want to compute something for the class. Okay? Like bounded maximum degree. Every graph has bounded maximum degree. But a class, I don't know, like planar graphs, they do not have bounded maximum degree. Even forests do not have. I think I'm ready to go for the next set of definitions. Yes. So, if I say, or we will revisit this after I define things, that will make it easier to do. Okay. That notation somewhere here, I will do that. But I need to say something about the notation, because I will speak about the notation. So usually this was our notation. For H is a minor of G. For shallow minor, initially I thought of this notation, which is a bit non-standard. Minor and D, but it's I will be using too many times, and Flohan will be using too many times, and he will hate me if I give this notation. So for that, because we are only speaking about minors now, instead of this, we will simplify it a bit, and we will just use D, G. So wherever this less than equal to sign comes in context of graphs, I will mean it is a minor, and the D will suggest that it is a D shallow minor. Okay? The notation is correct. So here what I am saying is this nabla D of G is a name, and the name is then there is a very stupid reason why it's written nabla, the story that Mohan told me. So this becomes grad, and in calculus gradient it has nothing to do with it, but it's also grad, and for that the nabla symbol is used. So you don't have to know that if you are not from mathematics background. There is something in calculus called grad, GRAD, and this is also greatest reduced average degree, grad. But that grad is gradient, this grad is this thing, but they use the same symbol, and it's a little maybe stupid or maybe it's a joke. No, it is just the edge density. So that is also another thing. In graph theory it happens a lot. Sometimes people use average degree, sometimes they use edge density. So they are kind of the same thing because of the handshaking lemma, only a factor of 2 here and there. But then all the inequalities become very strange sometimes. But there is no standardized.
But they have reduced, that's right. It is reduced.
Reduced.
Reduced it. Twice is not there.
Yes, price is not there. Reduced, I think it's because of this D shadow. Yeah?
Oh.
Yeah. I don't think it's for that reason. So you can always include a 2, and in all your calculations a 2 will be included. So clearly is a measure of average D. Okay. Now I want to define something else also here. So we don't know its name. So in the morning clause, I just did greatest reduced click number, because it's like how big a click as D shallow minor is hiding inside your graph. That's the measure. We'll have an M soon when we define it for family. So you can define it for any class, but it will make sense if you are defining a class of curves. So I'll tell you the names. No, it's still just defined for the class, and now we will go to the definition, another definition. And that's one of the main goals of today's talk. Let me just give the definition and then I will tell you what it is. omega thing is just definition. I will not speak about it much. It is this guy, nowhere dense, which contains locally bounded expansion, which contains bounded expansion. That is what your picture means, right? Flo, your picture means that, right? So, bounded expansion has a arrow to locally bounded expansion, means it's a subclass, and then locally bounded expansion is inside nowhere dense. So, nowhere dense is something bigger, and but our concentration is on bounded expansion. So, you see the workshop's name is Sparse graphs, treewidth, planarity, and bounded expansion. Last week we did not speak about bounded expansion at all. We spoke only about treewidth and planarity. Now we are here for bounded expansion. Today we are defining bounded expansion. Anyways, so let's see, what does this definition say? So let's go for bounded expansion first. So you have a graph, you look at the edge density of its d shallow minors. So whatever d shallow minors you can have, you look at their edge density. Or in other words, you look at their average degree. Okay? And those things must, so what we have, okay, so the supremum, the worst case scenario, the worst average degree you have among the shallow minors bounded by this d shallow minors, that is what you call your graph's most difficult part, or this greatest reduced average degree. So you are trying to figure out what is the most difficult part of your graph in terms of its. And then you are going to a class of graphs. You are saying that what is the greatest reduced average degree of this class? It is the worst case scenario you can have in terms of the elements of your class, right? So you are taking each of the grad of the graphs in the class and taking the supremum or maximum. Now, come here. We are saying your graph class has bounded expansion when if the grad of your graph class is finite or bounded by something. So how do I say that bounded? So there, in other words, there is a function from natural numbers to natural number. For each d, it is bounded by a constant. But the constant depends on d. That constant is exactly ft. Okay? So it never runs out.
So how about this class of planar graphs? Are they bounded?
We will see.
So complete graph is not for sure.
Complete graph.
Class of all complete graphs is not.
So how will it work? Yeah, but he wants a non-example. Yeah, so class of complete graphs. So what will this be? Or they themselves are quite high. Like one shallow minor, they are one shallow minor of themselves. So zero shallow minor of themselves. So already you cannot bound them, right? Like f0, you cannot put a value. If you set f0 to be 1000, then k1001 doesn't follow this bound. So it's not bound. Yeah, that's a good example. And similarly, the next one, which I will just speak about but not do anything afterwards, this is like how big a complete graph you have as a d shallow minor. That measure is this omega. Okay? But then you define similarly for a class, and then you say your graph is nowhere dense if that quantity for every d it is bounded. Okay? And that is nowhere dense. Okay. But I will not not speak about nowhere dense at all. I will prove two things. Let's see how much we can deduce from them. Okay. So then maybe many of these questions will be answered in many classes. But say it again, complete. But complete bipartites have big complete graphs as monarchs. Right? So if you take the set of all complete bipartite graphs, then in one side you put the vertices in gap, and the models will become somehow, these are like, the other side is very big, let's say, some 2 to the power n. This side is n, that side is 2 to the power n. Then I think you can find edge disjoint paths which connect each pair of them. So you can make a minor model.
Especially these, I mean, what is important is the edges and paths are short.
Sorry?
These paths are very short, that is the important.
Yeah. These parts are like two length 2. So it's it will be one shallow minor. So basically in this class you can find very big non-shallow minors. So you cannot bound, for example, F1 in that context. Okay?
Even for zero shallow minor, I think we are bounded, right?
Zero shallow will give you maximum. No, zero shallow will give you bipartite graphs.
Complete bipartite has like huge number of edges, like n square.
Yes, that is
That
true.
ratio is going to
So this will diverge. This will diverge. Yeah. So that's another way to think about it. I was always thinking about minors.
Actually, your argument shows that they even have huge shallow clique minors, which means they even are not nowhere dense. Your argument shows that, no?
Yeah. So even this will be unbounded. So it's possible that is bounded, but this is unbounded. Opposite. This is unbounded, but this one is bounded. But in that case, in our case, this complete bipartite graphs.
For bounded expansion, we only look into the grad, right? Not about the
Yeah, only the graph. So in nowhere dense, you want to exclude big D shallow cliques for each D, and here you want to just exclude anything which is dense
So if this
as D shallow.
is unbounded,
Yes.
if that is
Unbounded,
planar,
then
that
definitely
is
grad is definitely unbounded, but not the other way around. That's why the subclass inclusion is. Okay. So let's see what I have after this. Maybe I will delete something from here because I don't need these guys. And there is something of extension here. So time almost ended, but we started a bit late, so I will continue a little more. And we'll take a bigger tutorial with you. So, moreover, if f is polynomial, then C as on top of that, if C is that f, the function which I was bounding it with, this turns out to be a polynomial, then I call it a polynomial expansion. So somehow it requires a special mention because probably something more is coming, which we will be happy if it is a polynomial expansion. Right? Now let's try to prove a few simple ones. So I don't know which one to start with. Let's start with this one. So this has nothing to do with shallow minors, it has only something to do with minors. This particular level, but we will use it afterwards. So what I'm saying is G doesn't have a KT minor, then some function of T times the number of vertices. So the edge density is, or the edge density is bounded by some function of T. It doesn't have a KT minor. How do you prove it? So look at any vertex in G. This is your neighborhood of V. What can you tell about this neighborhood of V? So first of all, one comment is that I will use induction. What is the base case? Base is, let's take T equals to. Induction on, no, actually I will do, that was a good question because it's not usual parameter. So I will take number of vertices in G plus T. So K2 free means no edge. So number of edges is 2 to the power 2 times Vg. Whatever it is, it will work. There is no edge. The left hand side is just 0. Now, what can you tell about this NV? So this is KT minus 1 minor. Because if it has a KT minus 1 minor, along with V you will have a KT minor. Okay? So, yes, you are right. This guy is, or rather, if I formal, then this guy is KT minus 1 minor V. And let me call this guy G prime. So G prime is smaller than G in terms of this Vg and T, because this is KT minus 1 free, and of course the number of vertices is also less.
What is this vertex V?
Any vertex. Any vertex inside G.
But then you cannot like right? If you move an arbitrary vertex from V, then so that
Yes, because this is a arbitrary vertex of G. Look at its neighborhood. If its neighborhood has a KT minus 1 minor,
it's neighbor.
inside this neighborhood set, then together with the V, G will have a KT minor. Okay? So that's not possible. So I can say neighborhood of any vertex is KT minus 2. KT with minus 1 minor. Then let's use induction. So induction will say that number of edges prime is less than equal to 2 to the power t minus 1 times vg prime. We have this one. But how much is vg prime? What is vg prime? I can write it as just neighborhood of v. Okay. That's okay. Okay. Now you see, inside neighborhood of v, if I look at any vertex and look at its neighbor, that set is exactly the common neighbors of u and v. No, I mean some may go outside, I'm not drawing. I'm just restricting myself to the neighbor inside that white thing. What is now? What I know is that the edge count is this much for the whole thing. Okay? That also means that the average degree inside G prime is less than equal to 2 to the power t, because what is average degree? Eg prime divided by this guy times 2. So it will be 2 to the power t. So it is less than equal to 2 to the power t. So now should it be just a second.
You need not multiply by 2 for that. Each by being is only this.
No, but just for average degree I have to
It's not parallel.
Yeah, it's not bad.
How do you get the lesser to do and we are going to do it minus 1 at least?
By induction. By induction. In fact, I will get a little less because wait, I will get a little bit less. Okay. Just so what I want to say is average degree. But I want to somehow say this is strictly less. How do I say that? If you guys see that, it's tell me. So I want to say that it is strictly less. Somewhere I want to bring that strict inequality here.
But maybe the whole limit is strict?
No.
Because I think the base case was for strict.
Is the whole lemma strict? Okay, then let's try the strict whole lemma. We have strictness here also. Everywhere. Maybe you're right. So let's see how the calculation goes. I think minor model we can create. This one here. Right? So average degree less than strictly less than 2t. This also means this implies there exists u in neighborhood of v such that degree of u inside G prime is less than, strictly less than 2 to the power. Right?
The t.
No, 2 to the power. Yes? So inside G prime is strictly less than 2 to the power 2, which is the same as saying there exists U in neighborhood of P such that neighborhood of U intersection neighborhood of P is strictly less than 2 to the power 2. Right?
This is in G prime.
Which one? This one? No, here I don't need anything. Because G prime is the whole neighborhood of V. So you cannot have anything outside, any neighbor of V outside neighborhood of V, outside G prime. So I don't have to, that's the point why we do this. And then I can also change this guy a little bit. I can say there exists an edge inside G whose common neighbors are strictly less than 2 to the power 2. That is this event. This is what I want actually. Okay? So is that okay until here? Now I will draw some more features. So I will maybe get rid of this part. This part was just to establish that line. Now I have U, V, and some common neighbors, but that common neighbor is less than 2 to the power 2. Okay? And this whole thing lies in my big graph G. Okay? The initial graph G. Now what I am going to do is I am going to contract U and V. So this is G double prime. This new graph is G double prime. Okay. Now, this G double prime, because of the contraction, is now in the area of my introduction. So I have done a contraction. That means it's a minor of G. G doesn't have a KT minor. So G double prime will also not have a KT minor because it itself is a minor of G. So G double prime is KT minor, since it is itself a minor of G. So this implies by induction number of edges in G is 2 to the power P times, number of edges in G double prime is VG double prime, right? But how much is VG double prime compared to VG? VG minus 1. So let's write that minus 1. In fact, let's split that. Okay? Let's split that and write VG minus 2 to the power 2. Okay? In fact, do a little more. So it is EG double prime plus 2 to the power P is less than this get to EG double prime, how many edges have I eliminated? No. All these edges have one. These edges have two copies. Now it is a single copy. Right? So, strictly less than 2t, 2 to the power t, that means less than equal to 2 to the power t minus 1. So, I have forgotten about 2 to the power t minus 1 edges and also this uv. So, maximum I have forgotten about is 2 to the power t edges. Right? So, I can say this is less than equal. So EG is actually less than equal. Right? EG is less than equal to EG double prime plus 2 to the power t. And in the right side we have what we want. So thanks Rohan, you could prove it with the strict inequality.
So to do what T, how did we use? So I have marked T, U and V.
You had V which created these many parallel edges. I have deleted the extra parallels. So that might have given you to the bottom. Because we are only in single values. Dealing with single values. Okay? So is that okay? The lemma?
The reduction just on V, no? Not on mod V plus T?
Vg plus t, because I don't know, this works also. Sometimes I am reducing t and sometimes I am reducing v. So it's not a problem. Maybe you can do it with v also, but v plus t is safe. Well, I am not including v in g dash, so vg will go. Probably more. Okay. So, a few more minutes. That's it. I know, I'm left with one more thing. By 11. Go a bit faster.
Irrespective of what H is.
Doesn't matter. Yeah. Irrespective of what h is.
Minor.
Okay? Sorry. To the power h. So if you have a kt minor or k number of vertices of h minor, then from there you can get an h minor also. So in particular, if your graph is H-free, then it is complete graph on number of vertices of H free also. If H has T vertices, then it is KT minor in particular. But if it is KT minor free, then the number of edges is bounded by this function, or this function, 2 to the power t. T doesn't depend on D, that D shallow minor, right? It doesn't depend on D. So your F0, F1, F2 in the shallow minor definition, all are bounded expansion definition. These functions you can replace with 2 to the power cardinality of H. So it's actually constantly bounded. But constant also means polynomial. Right? Polynomial is much worse than constant, but we can say that G minor free graphs have polynomial expansion. Now, probably I will.
How did you get this in K mod H
If you have a K mod H minor, from there you can also get an H. So you have an H minor. So
no H minus or no K minus?
yeah.
Maybe we should remark that this is because when we take the D shallow minors, they're of course minors. Right?
Yes.
We want to bound the edge density of D shallow minors.
Mhm.
When we take the D shallow minor, of course it's the minor of the original graph.
Yes.
And of course it is also KH minor 3. Because when you take the minor, you're not
Okay.
minor of minor, you're
So what you are saying is that if I here I say H is so G is H D shallow minor free, then G is also K modulo H shallow minor free, D shallow minor free. Is that your point?
No, I mean just because, there's nabla D, just to recall the definition. Nabla D is the maximum density of a
Yeah.
shallow minor.
Yeah, maximum density of shallow minor. Yes.
So why, how can you conclude this? Because themselves they are KH minor 3.
They are
So by your lemma,
okay.
that's
Okay.
why the density
Okay.
is that to make it a bit more clear.
So the next one is, and this I will not put, this we will put as an exercise. So see G's, which the max degree of G is the then probably there are better bounds which exist, but for exercise, we can use this one. So it's the class of bounded maximum degree. Doesn't have a polynomial expansion. It has an exponential bounded expansion, but it is still bounded. So you see the function is appears here. Delta, capital delta is a constant. And the last thing that I will do in the tutorial probably. So these two I will do in the tutorial, but the second one was a bit important. That I can do. So we have done this before, that if J is a minor of H and H is a minor of G, then J is a minor of G. This is almost linear. But what we are saying is, if J is a shallow minor of H and H is a B shallow minor of G, then J is also a shallow minor of G, but how much? The depth changes, the depth becomes 2AB plus A plus B. Okay? But it still remains a shallow minor. And what in turn it gives us, the corollary, is that if you take a class which has bounded expansion, if you take all D shallow minors of this class, these are some graphs, right? These will also become a class of graphs. But this class will also have bounded expansion. This is what we do. And to create that F is something like this. So, yeah, I think that's all. If you have questions, please go ahead and ask. Or you can ask the tutorials also. The tutorial will start from 11:30 onwards.